I'll be honest here. I had a hard time summarizing this episode for you. And let's face it, it's all my guest's fault. Why? Because Aki Vehtari works on so many interesting projects that it's hard to sum them all up. Even more so because he was very generous with his time for this episode. But let's try anyway, shall we? So, Aki is an associate professor in computational probabilistic modeling at Aalto University, Finland. You already heard his delightful Finnish accent on episode 20 with Andrew Gelman and Jennifer Hell, talking about their latest book, Regression and Other Stories. He's also a co-author of the popular and awarded book, Bayesian Data Analysis, 3rd edition, and a core developer of the seminal probabilistic programming framework, STAN. An enthusiast of open source software, Aki is a core contributor to the ArviZ package and has been involved in many free software projects such as GPstuff for Gaussian processes and ELFI for likelihood inference. His numerous research interests are Bayesian probability theory and methodology, especially model assessment and selection, non-parametric models, feature selection, dynamic models, and hierarchical models. We talked about all that and more on this episode in the context of his teaching at Aalto University and the software-assisted Bayesian workflow he is currently working on with a group of researchers. This is Learning Bayesian Statistics, episode 29, recorded June 17, 2020. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the project, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private LBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
Hello, my favorite Bayesians. Before hearing from Aki, I have great updates to share with you. First, as usual, a grateful thank you to my brand new Patreon supporters, especially those in the full posterior tier or higher. Colin Caprani, George Ho, and Colin Carroll, thank you very much for your continued support. By the way, now you can choose to join the Patreon on an annual basis, and while doing so, until the end of 2020, you will get a discount of 2 months free of subscription. Second update, the podcast has a brand new website, living at learnbayesstats.com. When you take a peek, you'll see there is an integrated player to easily listen to and share episodes. Each episode now has its own URL for easier referral, and there is a mailing list form to stay up to date with the podcast's latest news and announcements. I'm super happy about this new website, so go take a look and tell me what you think. Third and final update, LearnBayesstats now has a Podchaser page. Podchaser is the IMDb of podcasts, if you will. So go ahead and feel free to give LBS a 5-star rating if you feel like it. Ratings help the show climb the ranks in categories, appear as a trending podcast, and help more listeners discover the show. I want to directly thank Yusuke Saito, by the way, who was the very first to leave a review at podchaser.com/learnbayesstats. I'm talking about good ratings here, of course, right? If you don't like the podcast, well, maybe don't rate it, but definitely recommend it to someone you don't like. Okay, that's fine by me. Phew, that was quite the update. As you can see, there is a lot going on behind the scenes, and there is more coming. This is, of course, thanks to all of you, So, as always, thanks for listening. Thanks for your continued support on Patreon. And I've talked too much now. Let's talk about model comparison, feature selection, and Bayesian workflow with Aki Vehtari. Aki Vehtari, welcome to Learning Bayesian Statistics.
Thank you.
Thank you. And did I pronounce your name with the right accent?
Yeah, it was close enough. It's difficult.
Oh yeah, H and R for a French guy, it's hard, but I tried. Thanks a lot for taking the time. It's an honor to have you on the show, and it's always great to hear from the STAN community. So as usual, I want to start by your background because you work a lot on Bayesian probability theory nowadays, but I'm wondering if you started there or were maybe your studies more applied and what compelled you to take this theoretical road.
So I was interested in computers as a kid already, and then kind of went to study computer science. Mm-hmm. I was also, during my studies, working in a company doing some software development. But then my friends took some courses on neural network. So Helsinki University of Technology had a long history in neural network research starting from 1970s. And when I saw what they were started to study, I was also interested in that. I studied many courses on neural networks and machine learning, and I did my master's thesis in using neural networks to solve inverse problem to estimate the material flow of paper pulp through industrial pump. And while I was doing that, I read Chris Bishop's excellent book, Pattern Recognition and Machine Learning. And there was like 2 pages about Bayesian inference there, Bayesian neural networks. And that got me interested. It was clear, I can remember the first time I mentioned my supervisor that, I read about this and this seems very interesting that I would like to continue on this. And I stayed with the same supervisor for my doctoral studies and then started learning more about the Bayesian neural networks. And it was easy in that way that Radford Neal had this excellent free software, FBM. So I could right away use Hamiltonian Monte Carlo to sample neural networks, and I could see right away that results were much better than without. And then it was just that I and my supervisors wanted to understand why this works better. But I was kind of convinced already because of these experiments, but then of course also when I kept reading, it felt like the very reasonable way of going forward, and in a way that there's just one way to make the inference. Model chain is the theory for the inference is the same. It's just a computational problem, how you make the computation. So I was working on this industrial project. So one of the main projects during my doctoral studies was then predicting quality of concrete. So there was a concrete expert who made these experimental castings of concrete with different types of sand or mix of sand used and different recipes. And then my task was to make a model to predict the quality. I started with neural networks, but then Radford Neal software had Gaussian processes, and there was a lot of, at that time, people comparing Gaussian processes and neural networks, and Gaussian processes just worked better. I had quite small data, and especially for the small data, Gaussian processes inference was easier, but they are specifically the computational aspects, but probably also for the small data, the prior on function space from Gaussian processes was better. And this then led me gradually away from neural networks and to Gaussian processes, and all the time more to Bayesian inference computation. It was also then that for the concrete prediction, it was really important that I know how good predictive performance my model has. Because if I say that 3 months after casting, compressive strength is something, and someone feels bridge based on my prediction, I really want that I know what is the accuracy of my predictions and whether can I say for someone that they can trust that the bridge will stay up. So this then led me to thinking a lot of cross-validation and model selection and these different diagnostics, model checking and so on.
A really rich introduction into what you're doing. And I can't help but notice that that's funny because actually everything that you're still working on today, you already worked on that during your studies. And these are topics that stayed with you during your career, like Gaussian processes and model comparison.
Yeah, Gaussian processes has been something that I tried to do less but somehow I get requests for help that are related to Gaussian processes. If I'm not seeking that kind of problems, there comes up problems that someone says that I noticed that, okay, actually Gaussian process would be here, good idea. Or now in Stan, that it's not easy to make Gaussian processes fast in Stan, but people keep asking that. So we did quite recent work also on that. Like, it seems that I'm not able to get beyond Gaussian processes that.
We're gonna get back to GPs a little later, but what's interesting to me, you started with the neural networks road, and then you discovered Bayesian stuff and Bayesian neural networks doing that, and then doing that again, you discovered the Gaussian processes. It's an interesting journey to me, and something that you told inspired me a question, which was, you said that you actually became interested in Bayesian networks because you were noticing that they were working better in your case than the Bayesian neural networks that you were using. Can you elaborate on that and maybe tell us when you think GPs could be more interesting than Bayesian neural networks in that case?
At that time, it was quite common for neural networks optimize and then adding some weight regularization or do early stopping of optimization. And compared to those, then the Bayesian inference, especially Hamiltonian Monte Carlo, did give us better predictive performance. And then in more difficult cases, adding to that, doing then ensemble of Bayesian inference, because in more difficult cases, then Hamiltonian Monte Carlo got also stuck in local modes. It's interesting that there's not happened much in with respect to progress of Bayesian neural networks since then, that like the most of the advance has been actually without Bayesian inference and just having much more data and mostly then just doing stochastic optimization, which has then the flavor of early stopping as a regularization. There's some very interesting work, of course, also now recently in the Bayesian neural networks. But specifically why I then moved away, at some point it was kind of possible to get similar performance with Gaussian processes, but then there were few cases where really this multimodality in the posterior in neural networks was kind of scary, that many of the chains did converge to similar results, but then like 1 out of 10 converts to different results with clearly different explanation for the prediction. And I didn't like that if I'm, again, doing recommendations and saying that something about how probable something is to happen, that if it's unstable with the computation and with Gaussian process, I didn't see that. So it was clear, easy to choice to move there. And it was kind of also the period of making then papers on computation or for Gaussian processes for different like extensions and different likelihoods and making them faster and things like that. And we were writing this GPstuff software, so on top of MATLAB and works also on top of Octave, which you could also say that actually it's kind of crude probabilistic programming type approach of building your Gaussian process model by combining different components and have flexibility in inference. And then we could do a lot of interesting modeling and these different projects where we use that and so on. And it was easier, the Gaussian process, to be like more pure Bayesian and trust that the computation is working. That's why I stayed there. Of course, it was related to that in the problems I worked with, there was not that much data, so there was no really big challenge scaling to massive data sets. And it would have been different path in early my career. There would have been massive data sets that I would have kept working more on neural networks.
Yeah, okay. Because you think that actually if the data you had at the time had been a lot bigger, then maybe you would have had more difficulties working with GPs and less difficulties working with neural networks. Is that what you're saying?
Yes. Maybe with these massive data sets, it would have not been that much issue of these uncertainties. But with the small data, it was quite clear that the integrating over the posterior was important and thinking about the prior and model structure and so on.
Yeah, plus maybe the less data you have, the more important it is to incorporate the uncertainty in your estimates and to be aware that, well, you don't have a lot of data, so really think probabilistically about your models and about your results. That's super interesting. And actually, this comparison you were talking about between Bayesian neural networks and Gaussian processes echoes a conversation I had with Elisaveta Semenova in episode 20, where we really went into the weeds of both techniques. And actually, Elisaveta told me there was a theoretical link between Bayesian neural networks and Gaussian processes. And I really didn't know that, but I'm not going to spoil it here. I'll refer the listeners to episode 20. Go listen to Elisaveta. She'll tell you all about that because I want to talk about a lot of other stuff with you. I have one last question about GPs, which is they are quite known for being super general, super useful, but also quite hard to fit to data. So I'm wondering, do you have like some guidelines for listeners about what the weaknesses or GPs are and where is the research right now about that? What are the novelties we have about these difficulties and improvements about fitting GPs?
One thing also that why I kind of stayed in Gaussian processes instead of like working in splines is that, again, what kind of data I had.
Yeah.
Splines are fine if you have small number of dimensions or additive nonlinear models are fine. GPs were nice when I just put everything in and have nonlinearities and all the interactions and so on. Of course, It is also possible to then get even more out if you can add more and more structural knowledge there. Like the GPstuff framework and then GPy and now GPflow, like these GP-specific frameworks. They can scale to bigger data, and like GPflow especially can scale to really big data. They are restricting that kind of type of models you can use. And then in a way that if you want to extend the model, you need to always then rethink also the computation. And so there's a balance between this kind of efficiency and general use. Then in thinking like Stan, which then tries to be very general in a way that you can write any model and you can just run the inference, then it can be very slow for GPs. There are things that can be made also in Stan internals to make it much faster for GPs, but it takes man hours to do that. So need resources, and we are getting there. We are going to get something. Stan is never going to be as fast as this GP-specific software, but we are going to get kind of the somewhere between compromise in flexibility and speed. Also, recently archived paper on then these like basis function approximations of GPs, where there's a strong connection to splines that we can handle then these low dimensional, let's say up to 4 dimensions cases and additive of up to 4 dimensions cases, which make also like certain uses of GPs in Stan much faster. In GPs, why I like is also that in addition of that, they can be used quite generally in this, like just put data in and have some flexible assumption on prior on functions. But that it is also possible to include more structural knowledge, like periodicity, monotonicity, like how smooth you assume your function is, and also them on top of then non-stationary mean functions, and that it's kind of the goes to that if we have that kind of information, we can really think of these priors in a function space, which fits well this Bayesian thinking. And also in a way that we can explicitly think about these, what are we saying in extrapolation? It's not just that we are smoothing data, that in some cases we need to really think carefully, what are we going to say beyond the data? And then it starts to be more important what we think about the prior assumptions outside of the data.
Yeah, that's super interesting stuff. But we have other topics to talk about, so let's switch gears. Before that, a quick question, and feel free to answer quite quickly, but I'm wondering how you became involved in Stan and in the end became a part of the Stan team.
So I had used Bayesian Data Analysis second edition book in teaching since 2003. And I've been following Andrew Gelman's blog. And then I had an opportunity to make 1 month visit to New York in beginning of 2012. Stanford had started 2011. And during my visit, it wasn't even that visible that they're working on that. Of course, there were some discussions. My visit was related to this talking with Andrew about model assessment, model checking, model selection. Yeah. And at that time, Andrew was working on updating Bayesian data analysis. He then asked at some point my help to finish the PDA 3. So I help with this model selection assessment, new parts, and also in the end there's these non-parametric chapters. And from that, it started our deep collaboration with Andrew. But it was also that Andrew's way of having meeting is that there's usually a lot of people in his office. When I was visiting there, also all these stand-related meetings were open, and I was just sitting in the office and then providing my comments, and in that way got involved by just commenting and language design and different algorithms, diagnostics, and then there was need for the stand dev team to say something about how to do model selection, and then leave-out cross-validation work kind of also got directed to that direction, and the end result being these Pareto-smoothed importance sampling, leave-out cross-validation, and loop packets, which has been very useful in Stan ecosystem, and also then parts of that implement also like in ArviZ packets in Python. And then it was also good that the Stan dev team has these weekly online meetings so that I could also then stay connected while in Finland. It also changed like what kind of research I was doing, because then getting involved, getting feedback from the users, noticed that a lot of these things that I thought were quite obvious, or kind of that there's no need for research because there's already some paper from 1970s telling what to do. But there's quite a lot of work going from papers saying something, how it should be done, and then having actual practical implementation in software, which is stable, numerically stable, and so on. So that way I got to, like many of the new research topics have been influenced by Stan users asking for help. The new version of RHAT, diagnostics, effective sample size, variational inference diagnostics, different variations in cross-validation, priors, and so on.
Yeah, that's funny to see all these parts coming together in your timeline since 2011. And actually, you mentioned the loop package. I think I saw that this package has been downloaded more than 1 million times from the RStudio CRAN. So congrats on that. It's amazing how many people you guys have been able to help with that. Actually, we're going to talk a bit now about model comparison and information criteria, but I also wanted to mention that I think you still teach BDA, but now BDA 3, right?
Yes.
And actually now the book is available as a PDF, right?
Yeah, for non-commercial purposes, the publisher gave us permission to put the PDF online. So I'm very happy that now all my course material is available online. Also, I have a plan that at some point I will also arrange this kind of online course open also for people outside of the university.
That's really a nice thing to do. I'd encourage listeners to check out the course material you have, which is available online. I think it's computer science MSc level.
Yeah, so in the Helsinki University of Technology, which was then later merged to Aalto University, the target student group is either advanced bachelor or beginner master level students. Yeah. And most of the students have already taken a lot of math courses, programming, and it is assuming quite a lot of prerequisites from the students, but my environment, it works nicely. If I would need to teach like the beginner in bachelor level or in social sciences, then I would use either Richard McElreath's Statistical Rethinking second edition or the new forthcoming Regression and Other Stories with Gelman and Hill.
Yeah, that's already a lot of good material, and yeah, actually now people can follow it up with the PDF of the book, so I really encourage listeners to do that. Let's talk now about something you've been working on recently, and which is a software-assisted Bayesian workflow. So what can you tell us about this workflow? How does it work? And also, why do you think workflow is so important?
Specifically, the software-assisted part is very much in progress. So you have also, like Mike Bedancourt was talking about Bayesian workflow in one of the episodes. And again, based on the user questions, user feedback, I see this problem that there's a disconnection between that we have books which tell about Bayesian workflow, like PDA book and Regression and Other Stories. And there are a lot of case studies talking about the workflow. But when a user is actually doing something with their data and they get, for example, a warning, it can be a bit difficult to find the correct material. Or even if they don't get a warning, but they get strange results, or what is the kind of the additional diagnostic they should make? And I think that there's a lot of this knowledge in these books and case studies, and also this tacit knowledge experts, data analysts have, that we can collect and make more formal and include in software. So there should be more cases where we can add more and more diagnostics which would detect that, okay, this situation resembles something familiar for which we have a recommendation. And then instead of just saying that, oh, there's a problem, also direct the user to additional documentation. So this is partly, of course, just the documentation problem, but also much of this that how we can add more of these kind of clever diagnostics, realizing what to recommend to do the next. There are additional levels that in some special cases we can have even more guidance. We might use these kind of software assisted workflow tools also in teaching, that there's some lectures, but then the students can start just analyze data sets, and we don't need to beforehand tell all possible cases what to do. Like we don't need to tell beforehand everyone what are divergences. But if eventually students come up with the divergences, we can guide what to do next.
Yeah, exactly. That actually sounds so useful to be able to do that, because as you say, teaching people everything at once is like impossible first, but also would be like super overwhelming. So you have to ease them out in there, but at the same time, you have to make people aware of what the divergence is, which problem you could have if you are not using a non-centered parametrization with a hierarchical model or stuff like that. Which are super important. But as you say, these are areas where potentially a computer could be assisting us and either doing the work for us, like in automatic reparameterization, like Maria Gorinova is working on, for instance, as we talked in episode 17. Or, as you said, like just even telling people, well, you have this problem, this could come from this, and here is where you can find more information about that. That would be super helpful, I think.
It's also that I don't think we can do automated statistician type of thing.
Yeah.
That you would give just the data and then computer would do everything else. But we really want that computer can give recommendations, but still the user needs to understand choices they make. And then that means that how we can connect to additional material. And in a way, the future plans for new books is also so that the new books have to be open access so that we can connect again our recommendations and to books which can then give more details on and more background on and justifications for these recommendations.
Yeah, this sounds awesome. And I really agree with what you're saying, which is like, there's also always this trade-off when you're working on a probabilistic programming language or framework like Stan or PyMC or TensorFlow probability, which is like, you have to have an API which is user-friendly enough, but not too much as to make people think that they can trust blindly the sampler and just hit the sampling button and just don't care about the warnings or else because the software is doing everything for you. But you have to understand what you're doing and the model that you're trying to sample from. You don't have to understand the nitty-gritty of HMC as you or Michael Betancourt do, but be aware at a high level of what is going on so that when this will break, you will be able to at least have a principled way of dealing with it. And I think you would say that this idea of a software-assisted workflow is really tied, as you say, to the diagnostics and that you get from the model. And I know you work a lot on that. So what can you tell us about diagnostics and what are the classic gotchas and maybe what are you working on right now about that?
So there are, of course, different diagnostics. Recently, I've been doing a lot of these inference diagnostics, like the popular RHAT diagnostic. We at some point realized that it actually has some problems, that it fails if the variance is not finite, and then had to figure out how to fix that. And then while doing that, also came up with these ideas that the usual effective sample size for posterior mean, but then the mixing of MCMC can be actually, kind of the speed of mixing can be different in different parts of the posterior. And so just reporting the effective sample size, one effective sample size for one parameter is actually misleading. That we should look at the effective sample size. For example, when we report posterior mean and then some interval, the interval endpoints, the effective sample size might be much smaller, which means then that the Monte Carlo standard error for the interval endpoints is also much bigger than what we would expect based on this effective sample size for the mean. And this is kind of what we want to also bring more out in this new paper, which is now in press for Bayesian Analysis journal. And then we have this implemented in stand-related packages and also available in ArviZ, these ideas. Also, effective sample size, it's some like quick summary to look quickly, but then in the end, the user will really look at the Monte Carlo standard error and accuracy for those quantities they are interested in. We have the related diagnostics for variational inference, which started because we have the Diagnostics inference algorithm. Soon we archive new paper on additional diagnostics for ADVI, these diagnostics for importance sampling. The other layer is then these diagnostics for model checking. It turned out that we can get useful information from this Pareto-smoothed importance sampling. Leave one out also as diagnosing model misspecification. Posterior predictive checks, which is old idea, but still like the new illustrations of how to use it has been useful. And in these different diagnostics, the challenge is, of course, that the diagnostics need to be kind of self-diagnostic. So if we have a diagnostic, it has to also diagnose when that diagnostic works. I think in a way that I'm between computer science and statistics. In my computer science department, I'm clearly on the edge of being like statistician, but my statistician colleagues think I'm computer scientist. And this combination comes in these diagnostics also that really need to think about what would be the mathematically theoretical, decision theoretically correct thing to do, but how we can implement it in computer which has finite speed, finite memory, finite limited precision for presenting numbers and so. And then all these need to be taken into account when planning these diagnostics.
That's a lot of work. Super interesting topics. And I guess that, at least in my case, in my workflow, when I'm using diagnostics, it's also because I'm comparing models. So I'm wondering, how does model comparison fit into your software-assisted Bayesian workflow?
It is very essential part because the workflow is not just for one model. Like the big workflow is composed of subflows. Like we have subflow just for design of experiment, prior elicitation, checking inference, looking at the posterior model criticism. But then one part is, of course, that if we find a problem with our model, we should then think about better model. That's one part where there can be then model selection. Is the more elaborate model much better? Is there need to use more elaborate and at the same time more complex model? Or it can be also that sometimes we can start with the quite rich model, like in variable selection, that we start with putting all variables in. But then when we, for example, it would be predicting disease risk. When we talk with doctors, it's better if we can explain the model with minimal number of covariates. And then there's another case where we can have large number of models and then choose some of them.
That's nice because you gave me a great segue for my next big question to you, but I want to talk about the classic gotchas and the limit of model selection, because I often see you on Twitter explaining some of that and it's super interesting. And what do you see maybe that are the most common misconception and mistakes about model selection?
Couple things. One is that the quite common thing when using generalized linear models is to look at the marginal posteriors. And that doesn't work well if they are correlating covariates, because then the marginal can overlap zero even if the joint distribution doesn't. And that's also a specific reason why I started to think about that we need to look at the predictive performance instead of trying to figure out directly from the posterior relevance of one of the parameters. Another thing is that if we have just two models, it's easier to do the model selection. But if we have very large number of models, and especially like in covariate selection, we have a combinatorial explosion of number of models easily, it gets difficult in that way that like predictive performance estimates, they have still some variability how good some model is. We have just finite data. Based on finite data, there's certainly some error in our estimate for the true predictive performance. And when we have more and more models, it's more and more likely that then we choose the kind of the model with estimated best predictive performance. We are just actually fitting to the noise in the selection process. So we need to think also about the selection process differently when we have very large number of models. So one approach for that, which was kind of pioneered already by Dennis Lindley in the end of 1960s, and then a few others had revisited along the years, is to fit first just one model which has kind of all the possible submodels inside. For example, in variable selection, so you would have all the variables included with some sensible prior, of course, on the relevance, like maybe regularized Hossu prior, if we assume that only some of them are relevant. But then we can use this big model as a reference, and then conditionally that this big reference model is making good predictions, we can do variable selection so that we ask that which smaller set of variables can give similar predictions as this reference model. Now we are not fitting anymore to the noise in the data, so each submodel is not fitted to different noise depending on which covariates are included, but they are all fitted against this reference model, which is kind of filtering out the noise in the data.
Yeah.
And it's then much easier to find good submodels. The selection process is not anymore overfitting to the data, and then better models can be found. And I will talk more about this in this seminar series talk 24th June, and the recording will be available afterwards on this seminar series webpage. The third point in the model selection is that after we have selected some model, how do we make the inference given the selected model? So like the Bayesian theory and decision theory is saying just that we should integrate over everything, but it's not saying that right away that what we should do if we select some smaller model. And this reference model approach helps there too. So again, the original idea is in this Lindley's 1960s paper that we can condition also that when we are using this smaller model to make predictions, that we can find out decision theoretically optimal way to use that smaller model to make the predictions conditional what we know about the big model. And that's a nice thing, and it further improves than what we can achieve. If we have just these like two models and it's not necessary go to these more complicated reference approach and the projection of the reference model to the submodel, with just two or few models, like the cross-validation can work. I'm often advocating cross-validation, but I also have to say that there's often, especially in the simpler models, there are many cases where we can look at the posterior directly. And the benefit of looking at the posterior directly is that it's also using the benefit of the kind of it's model-based, so there's less uncertainty. Cross-validation has the benefit that the cross-validation step itself is not model-based, like the M-open that we don't trust our model.
Yeah.
But then it has more noise in this comparison. And then that's why in these simpler cases, if there's no problem with the correlating covariates, for example, it's useful to look at also the posterior directly. There's a bit of information overflow that I try to tell about everything, that my sentences just go on and add more and more of these additional details. There's a bit of information overflow that I try to tell about everything, that my sentences just go on and add more and more of these additional details.
Yeah, but I feel that it's also good because it also highlights the fact that in the end, doing science is hard, doing statistics is hard, Bayesian statistics is hard. So let's take it step by step.
Yeah, it is hard that often the answer is, it depends.
Yeah, and multidimensional.
Yeah, I like that. If I say that I recommend something, it depends. So it's not unconditional recommendation, that there's always long list of like branching tree. And this is kind of the part of the workflow.
Yeah.
That it's difficult if the user needs to learn all the possible branches beforehand. But what if we can also guide along the way, say that, okay, now since you have many, many models, maybe now you need to think about alternative approach for the model selection and not just cross-validation.
Yeah, exactly. So I'm going to ask you one of these it depends questions, I think. And I'm really curious about that because you work on that a lot also, which is feature selection. Because I'm wondering, how do you include that in the workflow or even in your work in Bayesian statistics in general? Because, well, for context, for listeners, you work on this project called ProSpread, which is an R package to perform variable selections for generalized linear models. I'm wondering how mature these tools are and how do you recommend using them?
So the ProSpread is our software implementation for this reference model approach with the projection of this reference model posterior to these submodels so that it is doing both this improvement, reducing the noisiness in actual selection phase, but also doing the correcting for making the predictions after the selection. You mentioned that it's for GLMs, but we are also extending it. So the work in progress, the branch is in public Git repo already, but there hasn't been yet release for supporting also GAMs and hierarchical models. And we have also some papers on how to speed up also then this model space traversal, but in a way that these ideas can be used in more general. The ProSpread still is going to be a bit of limited in a way that what these submodels or the projected models can be. It already can be actually used so that the reference model can be anything. The reference model could be also neural network or Gaussian process or Bayesian tree forest, whatever you can come up. And then you could project it to GLMs or GAMs or these hierarchical models, which are then the inference or the implemented in ArviZ or VRMS. Right now, I can recommend then the current ProSpread release is useful if you have, let's say, at least more than 10 covariates. And then you can make first the big model either with like sparseness priors, like regularized horseshoe, or some PCA type of model. So we have papers on both of these. And then soon also, if you want to add nonlinearities or hierarchies, it will work. But the basic idea can be used beyond that. So we have also a paper on fitting that the submodel can be regression tree if we want to have regression tree type of explanatory explanations for complex machine learning models.
Yeah, and actually something I'm always wondering with this idea of feature selection, and that always makes me a bit skeptical, is can you still interpret the models with that? I mean, because it feels to me that maybe you're losing, one of the interesting part of the Bayesian workflow, which is the conceptual analysis you have to do before even seeing the data. And I'm wondering, well, if you let the data selecting themselves through the feature selection, do you lose these prior conceptual analysis? And then if you don't have that, how do you interpret the model in the end?
So of course we can, especially when there are not that many variables, we can think about the prior information and also these causal assumptions easily.
Yeah.
What I think that where these like the ProSpread approach is useful is that when we have quite large number of variables, and then we want to do this kind of initial selection that find the minimal subset of variables that have actually some predictive information. And then, of course, it's not the end that we've selected some variables. Then we still need to think about, are these reasonable? And if we are going to make any causal inference, we need to, of course, think about the causal assumptions for different variables.
Yeah.
But it might help that in a way that we can exclude some of the variables that, the data doesn't contain any useful information on this. There's one additional detail in the ProSpread that by default it is really selecting the minimal subset variables which can provide the same or similar predictive performance as the reference model. But then it is possible that we are leaving out that kind of variables which are highly correlating with included variables.
Yeah.
And so we are not saying that these would be all the relevant. We can do also the variant that doing this variable selection iteratively and find all the relevant ones. We have also prototype of interactive user interface that user can also see the the recommended model, but then seeing the variables when they have this domain specific information, they may say that, it would be much better to include this variable because it's easier to measure or it has better causal interpretation. And then what if we include this and remove this? And then they can see if the predicted performance changes or not. So in a way that it is also possible to let the user do modifications to the model, while at the same time we can guarantee that the user can't make such choices that would lead to overfitting.
Yeah.
So in a way, it's known that there's this garden of working paths, that there's a problem if the user makes choices that they might get overfitted, but in a way that we can also combine these ideas to a version of garden of working paths where they can't get overfitting.
Yeah. I have a ton of follow-up question about that. That's a very interesting topic, and also because it's very dynamic right now, a very dynamic area of research. But actually, I think I should do an episode dedicated to feature selection. So it will be for a future episode, definitely. And from your experience teaching this workflow, what do you think are the essential skills or maybe rules of thumb that you're trying to instill in your students? And also, I often ask my guests who teach, which mistakes do they think are the most common?
That's a good question, but also complicated to answer. So one thing is that when I was talking that I'm kind of working on these more of computer-assisted workflow ideas.
Yeah.
So we haven't yet been able to test them with students. So this is really work in progress. But then it was like where my student came from or what kind of background they had has been changing during the years. And at some point, then it was really kind of important that the course had introduced also project work, which then kind of combined these different workflow, like subflows, that they needed to use all of them in one final project.
Yeah.
If teaching just one thing at a time, it's difficult to see how these all are connected. So that's a very important part of the teaching. And of course, then the challenge is that when the students choose different kind of topics and different type of models, they will also experience different type of workflow. But of course, it makes it more interesting for them because they are also then working on some topic they find more interesting. But this is also like this project work and problems there have then brought up these ideas that actually we could make many things easier, that instead of first teaching something and then they make the project work and we would assume that they can remember everything we said before.
Yeah.
Also then the software they use would remind them. Mm-hmm. And so the challenges are that these different things get a bit mixed up in their minds. Even things like convergence diagnostics and model checking diagnostics will get a bit mixed up with some students.
Yeah.
That when the result is something that they can say that everything went fine.
Yeah. There are so many stuff to learn in all this workflow that I can see why people would make this stuff up. And also, you said that you're teaching to different audiences, and I'm curious about what your main teaching audience is. Is it like the people in computer science master that you're teaching, or do you have another focus?
Currently, the main target group is like beginner master level or advanced bachelor level students who have taken a lot of math courses and some programming. And in Aalto University, computer science students take also a lot of math. There's also math and physics students, engineering students have this background. I do get also students from business school and chemistry, things like that, but much less. And then, of course, those students, they have volunteered to take the course. Yeah. So that way, be different background. But anyway, because of this assumption that they have this math background, my course starts from the level that, assuming that's already in. One thing is also, I think that in quite many universities where there is some Bayesian course, there's a problem that there's maybe just one course. Like I'm also teaching just one course, but there should be many. Quite big course already in the bachelor level, but then also it's still not enough, this my course, to that they would have enough experience in many topics, that there are many important things that we don't have time. Only briefly discussing design of experiments and decision making. But these are kind of topics that could be topics for their own courses already. And of course, making causal analysis based on designed or observed data and so on.
Yeah. Actually, let's imagine that you are in charge of designing a curriculum for Bayesian courses throughout people's education. How would you advise structuring learning? Like if you're in bachelor level, then you have to master this. Then on the master level, you'll learn that and that. And then if you go even one level higher, like PhD, then you can focus on that in your learning. How would you structure that?
I don't think that's kind of categorization for the levels. Currently, it is also a bit of like why this is beginner master level. It's just that because in our university, I know that what courses bachelor students have taken before that. But of course, if there would be specific bachelor program for Bayesian statistics, it would be possible to focus more and then get earlier to the level like my course. And then there's also what is the target group? Since this is in computer science department, I'm also teaching about issues about the limited accuracy of floating points, so related to implementation issues. But if it would be bachelor program in Bayesian for social scientists, then probably there would be a bit less emphasis on these computational issues. Then it might be reasonable to at least briefly mention about these challenges. And of course, it is possible to start with easier tools like RST and ARM, VRMS, with easier to write models to get a lot going on before requiring to write models in Stan language. Or like in my course, students also implement Markov chain Monte Carlo algorithm because I think that they have the sufficient skills and then it is beneficial for them to realize this iterative nature, and it's not completely black box anymore what Stan and other probabilistic programming frameworks are doing.
Yeah, I see. It's true, at least in my personal experience. At the beginning, it's maybe hard and too overwhelming to indeed go into the weeds of implementing your MCMC and so on. So trusting user-friendly tools to do that is interesting. But then when you go on and try to tackle harder models that are gonna hard to fit to data, are gonna have divergences where you have to think a lot about your priors, then being able to at least have a high level of understanding of what the sampler is doing is really valuable. Yeah.
But there's no like one best way to teach Bayes, so that it needs to take into account that what is the background and what are the goals. Otherwise assumed like how much math or programming we want the same students to learn anyway.
Yeah.
And so that way, there are many different ways to plan and still go quite advanced things.
Yeah, that's true. Plus the fact also that Bayesian statistics often puts an emphasis on bespoke models and designing models that are really specific to the use case and to the field where you're working. So that means that you can't really teach like a general toolbox where people are going to just come and pick their most appropriate tool. It means that if you want to have a truly bespoke generative model, you have to have bespoke teaching techniques, I guess, for maybe as many fields as there are out there where you have to learn Bayesian stats. And actually, there is also an interesting blog post that you sent me on Andrew Gelman's website where you annotated a list of your favorite books, at least since 2018. And I'm going to put that in the show notes of this episode because I think people will be very interested in that. It's super useful. And that also gives a flavor of personally how you came from the neural networks world into the Bayesian world.
When preparing for this, I rechecked, and it's kind of fun for me to reread my notes on these books. Remember that really how great these different books were and how they kind of so strongly my influences. This is also something that when I sometimes see people say that they are self-educated Bayesians. So in my university, there was no Bayesian courses.
Yeah.
But I don't think I'm self-educated. I had great teachers. These authors of all the books I read are my teachers, and I'm really grateful that they all wrote these books.
Yeah, I agree. There are some very awesome educational resources out there. And you don't say it, but I'll say it. But the books you and Andrew and Jennifer and all the people who wrote PDA3 and all the books you wrote on your list are really awesome. And I think people are very grateful for these books. So thanks a lot, Aki, for that.
Thank you.
And Actually, you have another book coming very soon with Andrew Gelman and Jennifer Hell, which is Regression and Other Stories. We don't have a lot of time to talk about it here, but I don't know, something tells me that maybe you should come back on the podcast and we should do a dedicated episode about that.
Yeah, that's fine for me. But I can at least say here that the Regression and Other Stories, it could be the first book on regression. Emphasis is in regression and not on Bayesian inference, even if the code examples are using RStan ARM, top of Stan, and so it is Bayesian inference. So the focus is on regression and how to think about modeling. And so it should be out in July and all the code examples available.
Yeah. Actually, that's nice. I like the fact that there is not the word Bayesian in the title of the book, but as you say, the content of the book and the models are actually Bayesian models. And that's nice because maybe it will also show people who don't usually use these tools. Yeah, you can do almost everything you do with the classical statistics. You can do that with in the Bayesian framework. And actually, the Bayesian framework can be your default, and you don't need to have Bayesian in the title of your book to do that.
Other than Bayesian inference, the book really, it's not about how the computation has been made. So all these, what to think about, how to use regression and how to think about the models and background assumptions, that is universal.
Exactly.
Not depending on how the inference is made. So it is useful also for non-Bayesians, this book.
Yeah. Sounds super interesting. I can't wait to read that and to talk more about it with you. There is a difficult question, I think, to ask you because you work on so many different projects, but we talked about the difficulties, for instance, sampling GPs at the beginning of the show. And I'm wondering if there is like one or two common difficulties that you encounter with your models and data very regularly, and how do you usually solve these problems?
I don't know how to answer that. As you said, that I'm working on many topics, and maybe that's why I now like to say that I'm working on Bayesian workflow, because then I can list tens of different subtopics there I'm working on. When I'm working with other people on these applied projects, the biggest challenge is then the communication and the kind of how I can make them to tell me what they know.
Oh, yeah.
So sometimes because of their education, they have a bit of narrow mind of what can be done. And then they tell only those things they used to tell. And then it requires a bit of extra effort to convince that they should tell more how the data was collected, for example.
Yeah.
And what is the purpose of this? What is the actual question they want to answer, and not just what would be something that they know they could publish? And this is the most challenging part. And when I've been talking about computer-assisted workflow, this is also clearly one of the very advanced topics, that how we could do computer-assisted workflow for asking these questions. And I think that's maybe some kind of AI in the future could do that. But right now it requires a lot of human effort of these discussions. What is feasible from the modeling side, and what is actually known from the phenomenon, and what has been collected, and is it possible to actually collect better observations, and so on.
Yeah, that's super interesting. All these ideas about prior elicitation and so on, and trying to get people to really formalize what they know, as you said, about data collection, how data are generated, and even what they know outside of the data. And something I noticed was often that people clearly underestimate the amount of information they already know before even seeing any data. So like you have a lot of prior information, but we're so used to knowing this information that we forgot that it is prior information that we should put in the data. And I always have some fun doing that, trying to elucidate prior about that. And often you have people saying, oh yeah, I don't have any real prior on how these data are generated and so on. And then you talk with them and you tell them, well, but actually you're telling me that you think this variable could be a cause of this one. So that's a prior, so actually you already have a lot of prior knowledge, and we should put that in the model. It's always funny to see people realizing that.
Yeah, happened several times that first they don't tell that much, fit a model to the data, and then show that, oh, there's something strange. And then they right away realize that, yeah, of course, this is because of this and this. And then we can include that in the model.
Yeah, that's true. That's also the beautiful thing about having a Bayesian workflow, because you can realize that and then go back to the first step, the conceptual analysis, and so on. Yeah, and so on. Actually, we talked a lot about that with Avi Bryant, who is the creator of Rainier, which is a probabilistic programming framework for Scala. And yeah, we talked a lot about that, about prioritization and so on. It was very interesting. It's in episode 21, if listeners want to refer to that. Before I ask you the last two questions I ask every guest, I have another question for you because, well, you guys do a lot of stuff, the probabilistic machine learning group. So I'm wondering, what are you guys currently working on? And what are you personally excited about for the coming month?
For the coming month, I'm excited to have a vacation. So it's a beautiful summertime in Finland.
Yeah.
And soon I will be also completely offline for a few weeks. So, of course, I'm excited about working on Bayesian workflow and tens of things under that. This probabilistic machine learning group in Aalto Computer Science Department, it's a joint group with another professor, Samuel Kaski. And we are also part of this Finnish Center for Artificial Intelligence. And there's this excellent community of Bayesians, machine learners, AI people in Aalto and University of Helsinki. And we have also this bigger project advancing. So like in the one direction is improving modeling tools so that we can make models of how humans think, like the model of mind for the humans, which would then help AI better understand humans. And on the other hand, then thinking about AI tools for, on the other hand, helping like iterative model design or design of materials, design of anything. And so again, it's a big topic with a lot of different subtopics. But yeah, so we have soon opening call for postdocs. So if interested in any of these topics, we have a great environment and like a lot of people working on these so that there's plenty of people to talk with, interesting topics. And so recommend following, for example, my Twitter account for the announcement when we open this call for postdocs.
Oh, yeah, clearly. That sounds like a lot of fun. And I'll put your Twitter account in the show notes and then people can see when the openings are online. This is already the end. I won't do a 3-hour-long podcast, but I would really like to. So I have to ask you the last two questions I ask every guest at the end of the show. So the first one is, if you had unlimited time and resources, which problem would you try to solve?
World peace. But if staying in the kind of the scope, what I think I can actually do, yeah, I guess it's Bayesian workflow. It's a big project. If we think about all possible things, what kind of things Bayesian modeling includes, starting from like design of experiments to decision making. And currently it is beyond my resources that I can't solve that in, let's say, next 5 years. But of course, I hope also talking about these ideas, I will get other people interested in working on this. And of course, if there's someone listening who would like to come as a postdoc for me, that would be great if you're interested in working on Bayesian workflow.
Yeah, that's an awesome project. And don't hesitate to reach out to Aki, guys. So the second question is, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Andrew Gelman, because unfortunately I missed my trip to New York to the coronavirus situation.
Yeah.
It's very likely that it's also, I can't go there in autumn. And so it would have been great to have the dinner. And so that's my wish, that at some point we can also, again, continue our research discussions face to face.
Yeah, that's an awesome dinner, I guess. Let's try to organize that. Andrew, if you're listening. Well, it was such a pleasure having you on the show. I feel like we could go on for a long time. I hope listeners were inspired by your software-assisted Bayesian workflow, and I'm sure everybody is very grateful for the amazing work you and the whole STAN team do. I think it really helps popularize these methods and get people towards a more principled practice of statistics.
Thanks for the invitation. I feel I'm in a good company. I've been really enjoying the earlier episodes and enjoyed your style of interviewing.
Well, thanks a lot. That's the greatest feedback I could hope for. And as usual, I put resources and a link to your website in the show notes for those who want to dig deeper. So thank you again, Aki, for taking the time and being on this show.
Thank you.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.